No set agenda. The first 5 minutes of this, I'll be letting people in after I double check them against the list because I've had spam bot issues in the past. I record it. I put it online a couple hours after recording. If you're not comfortable with that, you know, log off now. Other than that, I don't have any set agenda. Last couple goes around, we beat to death interface call implementation details and, you know, why interface handling sucks now but didn't suck 20 years ago. It's all about getting hot megamorphic calls and inner loops of collections to run fast for Scala and other alternative languages. I'm all happy to move past that. And if anyone has a topic, just open mic. I ask that you mute your mic if you're not talking because we get background noise from everybody. And if you get 20 people, you know, you get too much. You know, today it looks like we're going to have, you know, 9. In the past, it's been about 20. So who knows? And more people may show up after a while. It happens. If no one has a topic, I'll throw one out. But I'm asking for topics right now. Otherwise, I'll okay. So sure. So here I am playing with a new programming language. I'm messing around with having true closures, where true closures means that the closures allow, you know, upwards exposed fun args, and you can modify essentially the hidden variables that are stored inside the state, stored inside the function state. And these kind of true closures can then be used to build like coroutines and generators. And a bunch of other stuff. So they're beyond Java's funcs. And they're definitely been around. The concept's been around for a long time. I wonder, anyone ever mess with languages with real closures? So like people code in this language, these languages. So Scheme is one of them. I think Haskell has them. I think Clojure might have them. I think Scala has them too, but I'm not positive because Scala backs on the JVM.
JavaScript has them, right?
JavaScript has them, absolutely, yes, and I use plenty of JavaScript. Okay, so do you actually use what is the upwards, what is the actual closure getting used for? I guess in JavaScript it's fucking used for modules. It's like everywhere. For a hidden function state where you're actually going to mutate the state. So the reason I'm asking is because the obvious implementation is that every time you make a function call, there's a malloc to go get some storage to grab the local variables, and that makes function call overhead fairly significant. And so there's a concept of pay as you go, and how you detect and decide that you don't actually have an upwards exposed fun arg, or you don't have a variable modification, and you can go to plain old stack pointer bump for a function call as opposed to doing a new. Like no comments. Okay, this is supposed to be a conversation, not a Cliff Does lecture. Here's Flavio. Let me pull another guy in. Assuming I can spell his email. Hi, Flavio.
Hey.
So yeah, I'm trying to get a conversation going about well, closures, implementation of closures and their practical use in the real world order, whatever that means. Who uses closures and why? Closures is closures, not funcs. So does Scala have real closures? Can I close over some internal state and then modify it later?
I'm not sure I understand the question. So closures, for me, like functions that could capture things from the environment, is that the definition?
Capture something from the environment, and then executing the function later allows you to modify the state and detect the modified state. So a generator. I have a function that I just call, and it gives me +1 every time, and it just counts up. Classic generator. 1, 2, 3, 4, 5, and then you feed it through some filters, and you get the prime numbers out because you do nested generators that check to see if your powers are blah blah blah. And there's a coding style that says, hey, look, it's generators, and that works because there's an internal state that keeps getting modified, which meant that when the function got made, there was a malloc, a new, that allocated storage space, right? And then when you executed the function, the storage got passed in to be modified, but you could have different such storages for the same piece of code according to where the function was made. I'm asking what's the use cases, because I'm trying to decide how hard to push on optimizing when no one, when you don't do this. One of them is I didn't escape the local scope, so it's all stack allocatable. And another one is I didn't modify, so I just left a pointer to the damn thing. As opposed to made a private copy or forced the variable to live in a new space or whatever the hell had happened.
So most of my closures, when I program, don't leave their enclosing scope. So they would usually either be called directly from the function within which they are declared, or they would be passed to like a map or something, but they wouldn't escape out.
Okay, so they have access to non-local variables commonly, but they don't escape out, so they don't have any lifetime other than stack.
Yeah,
fine.
So you wouldn't actually, you could get away with stack allocating everything.
Okay, is this JavaScript?
JavaScript, but I also did like Lisp, OCaml programming.
OCaml, yeah, okay, fine. Yeah.
Yeah, and in terms of optimizing this, I think if you decompose this slightly differently and you just say, okay, I have an allocation for the captured state, it's just explicit allocation. Then if you have generic escape analysis, which sees that this object which captures the state does not escape, so it can be scalarized and can be put on the stack. So this way you don't need to optimize this specific case. It's just, well, generic escape analysis and optimization of allocations which don't leave the scope.
You're saying do generic escape analysis as opposed to, okay, so there's no user annotations, like the user doesn't say, I'm making a local, as soon as you have a local new, you don't bother to have any variables.
Yeah.
And then you have a thunk. Okay, fine. Yeah, all right, this is what I'm heading down. I'm heading down the path of doing escape analysis, and I'm trying to decide, am I like over the top here, or should I just quit and back off? Because it's part of the typing system at the moment, and I'm not certain that I'm headed the right direction. Part of my typing system, sorry.
So, can you hear me?
Yes.
All right, so I also use the closures kind of similarly to how Mark uses them. So my language is mostly C++, and there's a different kinds of solutions for this. So you can use lambdas. However, similarly, I usually prefer not to let them escape for the obvious lifetime and memory management issues in C++. I generally avoid using shared pointers, and you can pass the state along if you use unique pointers, which is basically transferring ownership along the function stacks. And that's all stack allocated, no problem. However, you mentioned generators as your use case, and that is not what I would use lambdas for in C++. What I would use for this is basically coroutines. And coroutines in C++ are a little different than in several other languages. It's basically a relatively low-level finite state machine transformation. At least that's one way you can implement it. And then you can persist the state outside of your stack frame. So you can, of course, have a generator, which is going to be a typical textbook increment counter. Of course, in order to persist that state, you have to store it somewhere. And the basic method, of course, is to do a heap allocation. However, at the same time, there is a optimization of the coroutines, which is the so-called heap elision allocation, heap allocation elision. And this is basically very similar to what we just mentioned above. If you do not escape the use of your coroutine outside of a given stack frame, you can entirely elide the heap allocation and only use the stack continuing from the stack frame you have started on. So it's basically an optimization matter here.
Okay, so the first thing, C++ has closures, or does it have thunks? or maybe what you call lambda, how far down the rabbit hole does a lambda go?
So you can expose the function argument. So basically the way the lambdas are implemented in C++ is exactly as a function object. So function object in C++ 98 is basically a class which has a function called operator. And you can store the data in the class as ordinary data members. So the way lambdas are basically lowered to function objects in C++ compilers like Clang, for example. And the way that's being done, you have to explicitly say what you are going to capture and what is the evaluation semantics for the capturing. So you can capture the by value, you can capture by reference. Of course, this is to avoid the memory management issue, because if you capture everything by value, for example, you just copy in, and then you will never have any dangling pointers or dangling references.
Right.
So that's basically lowered to a function object with a function call operator and data members as captured variables.
Okay, yeah, it's been a long time since I've done C++. I Hotspot locked in on a very early version of C++ as the set of things that you were allowed to code into, and we didn't do anything else.
Right.
I didn't know that lambdas had showed up, but they sound like they're no more than thunk, so you can ask for them to be non-thunk-like if you also do something with memory.
Right, you can explicitly capture by reference, for example, and then you can pass this lambda outside of the function, but it's on you how you're going to...
Right, and it's on you to do the memory management. Yeah, fine. Okay,
right.
Makes sense. So when you do it, you're mostly doing lambdas that do not escape. So
there are basically several different methods. So one popular pattern, which I prefer not to use, is to use shared pointer. Then that's basically reference counting. I basically think of reference counting as a special case of garbage collection. And for my use cases, that's usually not a match anyway. So I prefer not to. The other way is to transfer ownership with unique pointers. So this is a little bit closer to Rust. Unique pointers in C++ only have move constructors. So you are not allowed to copy them. So you have to move it. So compiler will check whether you have actually moved the lambda out of the function, and then you are not allowed to refer to that lambda inside the function. So you could basically try to move the elements from the stack frame to the lambda object and then move the lambda object out. That has its own trade-offs in concurrency. Oftentimes it's not such a bad idea to actually partition your data and just do the copies by value, because even though you are going to take the hit to have the copy overhead, then you will not have to worry as much about concurrency issues, data sharing, and all that. But it's all trade-offs. It really is use case specific most of the time.
Yeah, gotcha. Yeah, I see the C++ 14 hotspot, but I highly suspect that 99% of the code won't actually change there, mostly because, there's a lot of code and a lot of it's kind of delicate. So it'd be nice if big chunks got rewritten, but I don't know, I'm not holding my breath.
So in Scala, we have very flexible lambda, so they don't have much constraint. You can easily capture mutable values or immutable values. It doesn't bother. And in the end, it's just like syntactic sugar for generating a class for a functional interface, right? So it's just an object in the end.
So you do an allocation?
Yeah.
I was trying to decide how much effort was it worth to remove the allocation, to optimize away the allocation, right? And in this case, it sounds like you're probably punting to hotspot and see if hotspot will do escape analysis. And that was part of what Graal was having good luck with, was escape analysis, accelerating Scala and other languages that were sort of allocation intensive. So my cat is stir crazy here, or cabin fever or something.
I think for Scala, at least like the systems I work with, the main problem is the lambdas escaping because of the composable APIs that I explained on the last meeting. And then having to allocate all the functions, and then having to invoke through invoke interface, and etc. So that's like for Scala probably the biggest issue with lambdas.
Yeah, right. Yeah, no, it becomes right. becomes a sort of fairly language-specific optimization problem to go spot the pattern you're using to construct the nested lambdas and know to inline them sufficiently that they all become constant flows that turn into basically execution. It's a different IR ultimately. And this comes around a bunch of times in the other languages too. At some point, you're trying to write a language in a language, and then the underlying support machine doesn't understand what the hell you're doing, so it gets conservative on every possible thing. Yeah, there's no good API for the compiler level, which in this case, if you're talking through bytecodes.
Truffle in Graal is supposed to be the way to handle this kind of thing.
So it's not Java bytecodes. You're going to write to truffle IR.
No, yeah, as far as I understand, there's some programmatic API, and you just write your interpreter in this way, and it lets the whole system know that this is an interpreter. It needs to be specialized for your input. So this way, you compile it as you produce the compiled version of it.
Yeah. Okay. Just not yet mainstream in any significant way.
Yeah, and as far as Scala and monadic interfaces composed of APIs, that's something that's happening at the user level. It's not something that Truffle would solve.
I think the suggestion was that Scala would cough up truffle IR directly as opposed to Java bytecodes.
Yeah.
Yeah, so that's the thing. Like, you can do that at the language level, but the interaction and the dynamic nature comes from the user code. So it's a user land interpretation thing. It's not
right. You're building, right. I understand. You're building a user land interpretation mechanism, building basically a user land interpreter. What I heard Arthur say is Truffle supports the notion of an interpreter. Somebody at the translation layer has to make it go to Truffle. Okay, so what you're saying, Flavio, maybe is because I'm writing it in Scala, I actually have to have the Scala code talk to the Truffle API directly, not talks to the Scala C compiler, who then talks to Truffle. This is, God knows, fourth, the stupid language fourth from 40, 50 years ago. It was my first like programming hack. The compiler is baked into the language directly, and you wrote DSLs by directly talking to the compiler piecemeal as if it were a compiler. You talk the IR to the compiler. And that concept's come and gone a dozen times in programming languages. It always has the problem that you really have to be very much in bed with what the compiler API is in order to use it. Whereas people do DSLs all the time where they just write little miniature languages, like printf, freaking the format parser is a little miniature language. And no one wants to go learn a compiler IR in order to go write printf. So it's kind of that concept's been around a long time, and it's not heavily used because I think it requires too much expertise use on the programmer. And maybe there's a better way there somehow, but I don't have it right now.
Yeah, so my initial attempt at solving that problem was with a method fusion approach. So basically you have the just-time compiler apply transformations that fuse, if you have like a chain of 200 maps, right? Map calls, somehow be able to compose of the functions, and then make sure that they don't escape and etc. But Hotspot has too many limitations to do that.
Yeah, Dave's asked for links to Truffle, so throw a link out there. It's just easy to Google Truffle.
There's so many truffles, especially
okay, fine.
With the mushrooms.
Graal. Do Graal. There you go. Graal and Truffle. That's what you're looking for.
Thanks. I want to be able to follow you a little bit better. You're very deep. I operate at a higher level, so I came here to broaden my horizons.
Oh, okay. Well, we haven't talked any CodeGen at all, and since I started doing this thing, it's still pretty operating at a pretty high level. I don't know if anyone actually does CodeGen anymore. So everyone's using like Hotspot or C, and the C crew, and the Hotspot code generator is moving very, very slowly. Actual code generator is moving very slowly. So I don't know if anyone's actually doing code generation here at the machine code level. Register allocation. You want to do register allocation? Anyone done register allocation in the past? Not doing it now. No, fine. Instruction selection.
I recently wrote a new ADL rule in C2, but that don't know if that really counts. It's just emitting a call.
I'm sorry, you wrote a call to C2 to do what?
No, I wrote a rule in C2's ADL, but it just emits a call. So it's pretty simple. I'm working on native downcall and transfication for Panama. So basically in the IR, we generate a custom native call node, and then we have arrays that hold the registers. And then on one of the virtual calls to this node, C2 gets these registers, so that goes into the register allocator, and then we just emit a call for the node. So there's a little bit of code generation going on, but not that much.
I'm sorry, tell me again what Panama is?
Panama is basically a different way of doing native interop from Java.
Oh, okay.
Different from JNI.
JNI has some overheads. Wow.
Yeah. I saw one of your talks about this as well.
Yeah. If you get the target method to make promises about what its behavior is, you can clear out like 90% of that overhead.
Yeah. So I found through benchmarking that a lot of the overhead comes from the thread state transition doing a volatile write when you come back from native. There's like, we transfer from Java to native so that the GC can do its job. But then when we come back, we have to kind of hop into a save point right away. But this is not an atomic operation. So it writes, first it writes a flag to say, I'm doing a thread state transition from native to Java. And then it does the actual thread state transition. And the volatile write is costing a lot. So one thing we've been looking into is
just around x86.
Yeah.
And how do you know the volatile write is costing you a lot? Because an x86 will like throw that thing in a store buffer and queue it behind a bazillion other things, and it should pipeline really smoothly. Like, where do you get the notion that the volatile write is the issue? It could be. I mean, I'm not saying no. I'm just like, where do your numbers come from?
Well, now that you say it, I'm thinking I've benchmarked the function with and without the thread state transition altogether, right? So for trivial functions, we can just ally to thread state transition. If you're accessing some memory.
Okay, so thread state transition is expensive.
Yeah, exactly.
And you're thinking it's the volatile write.
Yeah.
This is like a VTune question. Because without a hardware performance counters to blame the right thing, you'll blame the wrong thing. Okay. At Azul, I got the exit from native call down to a single store, and it was volatile, but also x86 has the semantics you want for a store, for volatile store. So you just on the x86 you just do a store. In my case, it was store the stack pointer down, 0 over the stack pointer. It was an atomic race with the GC to who claimed the stack pointer.
Recently there were some changes in this code. I was not involved, but we did some further optimization there. And actually, this volatile store was causing some difficulties.
So what's the implementation on x86 for volatile store here? Is it just a plain old store op, or do you have to have a fence?
I think it's a log add.
You have to do a lock store.
Yeah, so it does, I believe it just does the store, and then it does a log add RSP 0, so it just does to do the flush.
Right, yeah, so you have to have a lock. Yeah, that'll cost you. I don't know, Azul just did it with volatile semantics and a 0 store. It was all fine.
Is this open source?
Yeah, this code should be. I know Azul open source their almost all their code. This goes into, I redid all the thread handling at Azul to get the low latency and the safe pointed everywhere kind of game. And part of that was looking hard at the transition. So the biggest mistake was you couldn't get the stack pointer and program counter from the OS. The GC can't ask the OS for a stack pointer and program counter of a remote thread and reliably get an answer. One time in a million, it will get crap for an answer that will pass all your thresholds and you'll die. So, and actually, in most OSs at the time, in fact, years later, I got confirmation the situation's still fucked up even as of a couple of years ago. You'll get crap for answers fairly commonly that you have to filter on, but even at some point, you pass all filters and still die. So at Azul, at least, I went through and said, I explicitly store down the stack pointer if I want the GC to touch it. And then explicitly CAS, I believe I think you're correct, I have to do a CAS to reclaim the stack from the GC. And so that requires a lock for Azuls too. And I'm trying to remember on the x86, I swear I got away with a plain store to take it back. Yeah, see, I see this as sequentially consistent atomic. I needed atomic, but not consistent, not sequentially consistent. Because once the GC claimed or the thread claimed, you know, he didn't care what the other guy saw because the other guy was going to lose the race, and then the loser was going to do something slow to go get his consistency back. Okay, fine. I don't know. I'd have to go look at my old stuff here and see what goes on. You're right. There was a CAS involved to reclaim the stack, a locking operation involved to reclaim the stack. So lock of, but then you get the offense, and then you suck. And that's because you have to do concurrent GC. So if you want to call native code and you want to allow concurrent GC to crawl your stack, native code has to promise the stack's crawlable in a sensible way. In particular, it doesn't touch any pointers is the obvious one.
Yeah, so for Panama, you can't pass any Java objects down to native. It's all just native.
Right, you can't pass any Java objects in. Right.
Yeah.
Yeah, then it works. Yeah, then it works. Because you don't have to have a GC lock to oh no, it's the other way around. If you promise you don't block, then you're not going to start a GC cycle and crawl your stack. And if you're going to, oh, okay, no, that's fine. Yeah, you can just store the stack pointer down. And then if the GC wants to crawl, he starts above the native call because he's got the stack pointer that you store down. And when you unwind, you clear it and say, you know, my stack's back in motion again. But the GC never claims your stack behind your back. And then you don't have to take a lock.
Yeah.
So this was the most expensive thing. I thought this was, what era x86 is? I thought they got this thing down to an L2 hit. So a dozen clocks.
It's only a few nanoseconds anyways, right? I think.
Well, yeah, right. So it's a billion. If you make a native call a billion times a second and you burn a bunch of nanos per billion, then it adds up. So the question is it just a few nanos still? And this is what you're interested in clearing out?
Yeah. It's mostly just exploring to see what we can do here.
Okay. Fine. Like, what's the use case for a billion native calls a second? My cat is howling the howl of death for no good reason.
I guess use cases would be if you call into native to access some native pointer, but at the same time, we're also adding a native memory access API anyway. So
you get unsafe. Isn't that your native memory access API?
Yeah. Sorry?
Unsafe? Isn't unsafe native memory access API?
Yeah, unsafe, but unsafe is not for everyone because it's unsafe. So we're adding a safe version as well.
Okay.
That is maybe a little bit better typed as well.
Okay, so there's an in-between state where it's not just peek and poke and shoot yourself in the foot, but there's something that you can promise me about the native pointer that I can load through that's not causing security issues.
So there's safe operation modes and unsafe operation modes, but basically in the safe operation mode you have basically a liveness flag that is being tracked and spatial bounds as well. So before you do the access, it's checked that the memory is still alive and your access is within the spatial bounds, and then does the access. And this hoists out of loops pretty reliably. So yeah.
It's basically, when you make such a native pointer, you actually make a native chunk of memory, and then you're going to bounds check it.
Yeah.
Yeah. Okay, that's fair. That makes sense. So this will help like memcached folks and the like, right? This is folks who off-heat big storage, graphics card buffers, network buffers, the like.
Things that currently use direct byte buffers.
Yeah,
but those are alt mutable. So yeah, and they have because they're indexed with integers, they have a size limit as well. And also there's a bunch of, right, if you allocate a direct byte buffer, for instance, and there's no more space, it tries to just go into a busy loop to wait for maybe the GC will clean up some other direct byte buffer and we get some native heap back, and then we can do the allocation. And then when you deallocate, you know, there's a cleaner thread that has to come and clean up. So one of the goals of the memory access API is to have deterministic deallocation. So you allocate and then you say close now, and then it cleans up the memory.
Yeah, this is the whole difference between finalizers and, you know, C++ destructors, right? There's no user lifetime management at the Java level, unless you hand roll ref counting or whatever the hell.
Yeah.
Yeah, I've ran into this too. Run a big IO bound, complicated big data, so it's reading big IO, and you run out of direct byte buffers all the time. And so what? Hey, why am I leaking direct byte buffers? Oh, sometimes no, the finalizer hasn't run yet, or the cleaner hasn't. So you end up hand rolling all the, delete the DBBs so you can reclaim them immediately, or have to do special heap flags to have more direct byte buffers and whatever the hell. It was like there were holes in the clean Java, you know, API where the real world was leaking through, and needed some love.
Yeah, one of the problems I've seen as well, because I also tried something with where I allocated a stub in the code cache and then attached to Java object with a GC cleaner, and the GC just didn't clean up the stub because there was no Java heap pressure, and the GC can't see that there's actually a bunch of other memory attached to this Java object that it needs to clean up.
Right. No, this is a different thing I rant on all the time, which is, you know, GC is a lousy way to manage your program's caches, because GC has no clue you're running a cache or what the semantics ought to be, or could or would or should have. And I have hit any number of real world issues where people were managing GC with caches, including inside the JVM itself. It's not the first time I've heard this story. Hit it all the time at Azul. So we just, because Azul had this, you know, concurrent collector that was cycling full GCs very rapidly at very low cost. That's how it works. And that meant anyone who did anything where they did a full GC cycle to clean something up, got it cleaned out from under them constantly. So we had people who didn't understand why they threw something in a cache with a weak ref and it was dead. So the next clock cycle, the GC stripped it out. We had to screw around a bunch, but you hit it all the time. The other version also happens where the GC doesn't know that you're running a cache, and your cache is big and it's full, and the GC decides he needs to clean some weak refs out, so your cache gets stripped out. But now your cache is not caching, and because your cache is not caching, you do all the work to reload the cache, and all that work requires a ton of GC. So the GC runs, so it flushes your cache, and you get a vicious cycle where you can't cache anything because your cache gets stripped because the GC is out of memory all the time. And so you get a very bimodal, server performance issue where the cache is full and the GC is lightly running and everyone's happy and it runs well, or the cache is empty and never catches up because the GC is furiously GCing because you're doing all the work, the cache isn't caching, and so you keep flushing the cache, and so the server is either high or low, and you can't get from one to the other without basically rebooting the server. It's a very this is a standard classic fail and control theory. Do overdamped systems or underdamped systems control theory, you discover this kind of shit happens because there's no feedback signal between the GC and the cache. And the GC should not be taking feedback from caches. Caches should not be driven by GC. There are other things you use to drive a GC, that drive a cache that GC is part and parcel to, but having a GC drive it directly is not the right way to go. Fine. So what else? No one doing CodeGen. No one doing register allocation. People doing cough down to bytecodes. We had well, people who scholars here. Everyone here like doing things with Java and or Hotspot, not Java, Hotspot and bytecodes. I know people do other stuff. Why are you here? Kipley, you took your mic off. What are you going to say something?
Oh yeah, I was just thinking like GodBolt exists, and I would think about the complications of getting a GodBolt for JIT compilers. And I can think of a million things, like tiering would get weird. All the OSR would be weird.
I'm sorry, what did you say?
GodBolt, the like website where like you get all the assembly output for compiled code.
Well, I heard GodBolt twice now. I never heard the word before.
It's
It's
actually the name.
I've seen it so many times. The compiler explorer, sorry.
Oh, this thing. Oh my God.
Yeah, you feed it code and it feeds you code.
No, I have not played with this thing.
Anyway, it's really cool because it's like a really easy way to check if like a language does a certain optimization. And it would be really fun if I could play with this with JITs, but also really hard.
I will mess around with it because now I'm curious. So put it on my links here. I'll go screw that later.
That reminds me of the old days when we used to write C or C++, and we had a integrated development environment with a debugger that allowed us to expand the source code into the assembly instructions and then do those and watch the registers change.
Nice.
CodeView, I think, maybe Microsoft CodeView had that feature.
Yeah, okay, fine. Yeah.
And it was fun to be working at that
Lisa.
at that level.
Oh. Sorry.
Something I was thinking about in particular is that GodBolt lets you feed in LLVM bitcode. And if I could like get some reasonable comparison of like LLVM bitcode compilation results to like Graal Sulong compilation results, that would be really interesting.
Yeah, this is like comparing code generator things. It's actually really tough to do reasonably well because you're mostly like there's a few special things where one wins and one loses, but mostly you're looking for broad scale statistical value, quality of the code as it's run through the millions and billions, right? So it's useful to look at little bits and pieces because you want to know how somebody did something, but at the same time, it's commonly the case that compilers will commonly, I want to say, fail to do what you expect in the little bits and pieces kind of domain because they're not optimizing for some custom little tiny corner case that you've accidentally fallen into. And instead, it's all about, you know, what do they do on average over billions and billions of lines of code? But definitely it's fun. Back when I was doing a lot of code gen, I studied the assembly all the time. And now you brought that up. So one of the things I did at Azul was I put a little tiny web browser in the back end that you could then get all the guts of the JVM to come out as web display things, HTML pages, including very specifically JIT'd code. Eventually got to the point where it dumped out the machine code, the assembly, the Java lines that matched it using Java variables and the types the compiler annotated, along with hardware performance counters, all as a file of assembly for your favorite method, along with the internal profiling data, right? So you say, my hot method is X because I profiled, and therefore there's a link on the JIT'd code page, and I could click through and see the JIT'd code for every possible method plus inlines and whatever. Very, very useful for doing performance work. Azul now sells that as an add-on, I think, as a thing, and I miss it from the JDK days, or from JDK doing this thing. It's very useful.
Are you talking at what is called ZVision now?
I guess so. They changed names 3 or 4 times. And then they'd add a bunch of layers to make it, in my head, difficult to set up and use. I just had a web browser coughed up bare HTML. It was instantly quick and instantly reliable and told me the state of the machine I was trying to debug, the virtual machine I was trying to debug. Very, very useful.
Yeah, I think another alternative for this compiler explorer for JVM would be just writing small JMH benchmarks and using perf_asm, so it would spit out the assembly annotated with counters.
But you have to use JMH.
Yeah, but
Okay.
like it's the easiest way to see the final assembly for a small snippet of code you have. But then in order to interpret the results, like you need to understand why this happened, because yeah, there's a lot of moving pieces like profiling, CHA, things like that.
Yeah, yeah. Now, if you start with something that looks like simple C code, you usually get the obvious assembly out. But as soon as things start to ramp up, it gets complicated fast. So what is this GodBolt thing actually doing? Oh, policy. Oh, God. Ah, I see. Whose compiler are you using? C++. I'm poking at GodBolt for a second here.
They added Zig too, and Zig seems like a really, really fun language as a compiler. So it seems like internally, they tried to make all the compiler internals asynchronous, and it just looks really funny. I don't know how else to say that, but so yeah, Ziglang.
Throw a link out.
Yep.
Ziglang. See, I'm writing a language, doing compiler research, so I'm always looking at new languages and how people do things. Okay, another link. Thank you.
So Zig is also a C compiler, which is the really cool part. I actually know some people who are like building OS things that I don't understand, but they're actually able to compile this C with a Zig, and it saved them a bunch of time and like the usual problems of running C programs and getting everything installed properly.
Okay. Yeah. Yeah. Okay. Safety or not? Speed or not? A few extra things. Yeah, fine. Okay, I'll take a look at it later. It looks good. Coroutines. Yeah, you mentioned some stuff. You said they're compiled down to like a little state machine. I'm not sure what that doesn't jive well with my concept of a coroutine. So I'll take a look on that one too. Zig is also a C compiler. Yes. And in JIT'd. Yeah, fine. Okay. So one of the lessons is the next runtime I do. Should I do another one here? I guess I'm in the middle of doing one. Definitely, I'm going to export assembly code and all the profiling internal JVM state. Not necessarily, and programmatically, so somebody else can write a browser reviewer on it. Not necessarily let you edit the state, because that doesn't necessarily make any sense, but definitely let you programmatically look at the internal state of the world. Okay, what else?
Tell me if this is too high level, because you're really talking about low level compilers, memory allocation, and closures and all that. But I've recently started using C# because I'm doing Unity programming, which is a really cool 3D graphical game environment. A lot of pro games are made with it. And I used Java for a while and Scala for a while, and I'm noticing that these languages seem to be influencing each other. And I'm sure someone's done a study and understands these things. So C#, Java picks up features, functional features that look like they came from Scala, and then there's Kotlin that's around now. And so first of all, tell me if you reject the idea for a conversation suggestion, and then maybe we'll go on.
I'd have shut it down already if I had.
Okay, good. So I'm curious, how are things, is it the same mix of people that are developing these languages, or how are they influencing?
Oh, people talk to each other. Yeah. It's just like make a better world, right? So you go say, hey, look at this cool thing I'm doing, and so I read other people's cool things. Hey, I'm going to go read Ziglang and GodBolt today, right? Fine. okay, well,
Yes.
since I write stuff on the, you know, I go give talks the world over about whatever stuff. Often it comes around about Java made the following design decisions when they made them. And can't we do better, right? And so a bunch of people come along. Hey, Lisa. Sorry, the cat is
I'd like
howling
to
the
see
death
your
howl because she's alone, because I'm not petting her even at this very moment.
We won't
My
mind
wife's
if
in
you
the
do.
shower, so I, you know, sorry.
It's
Yeah,
fun to see
right.
people's
So,
pets. But go on, please.
yeah, right. There's a lot of sharing. It's not that there is any sort of closed circle of sharing. It's just, you know, I throw it out there, other people read it, other people throw it out there, I read it. So functional programming has been around a long time, predates Java, obviously. Scala showed that you could do functional programming on a JVM. So, you know, then Java became wildly popular, and there's a large enough fraction of people, you know, take millions of programmers and billions and trillions of lines of code, and there's enough effort to go, enough people want to see something better happen, say, okay, you know, other languages do this, why can't we? So Java picks up these features because there's engineering effort spent and because, you know, there's a push. Yeah, there's communication goes around. It's not like I'm talking to the C++ designers and they're talking to me directly. It happens, we see each other at conferences, but that's not a design choice or decision. It's just interested in the same domain, talk about the same kind of stuff. What's this other guy doing? Oh, he's doing this thing. I'm doing that. That looks cool. I'll do some of his. He'll do some of mine. Fine. So yes, these ideas get cross-pollinated.
For example, in C#, there's something that looks quite a bit like annotations or Python decorators. And that's one way that you can communicate in your code. You can kind of describe your public fields such that the Unity environment can expose them in its user interface. So for instance, you can drag a slider to adjust the number of spheres that you're going to generate in the world or something like that. So I hadn't, and you know, Java didn't have annotations prior to, what was it, Java 5, I guess. And so, you know, when did C# come up with them? And so I'm just...
You know, C had annotations, pragmas of various kinds, right? And they came in the compiler directives, and they came in the special comments. And so the concept had been around the programming community long before Java, right? So Java came along and did what it did, and then people were like, yeah, I want to write Java doc. Okay, I can't do it as a compiler annotation, something as a funny comment. But then there were folks that said, well, I actually wanted to say shit like, this variable should always be locked, and it should, you know, I want to specify somehow more hints to the compiler or lessons, or this is always null or not null or whatever. And even if the compiler doesn't directly do anything with them, I'd love to run a different tool that could parse the code and read these annotations and add extra language semantics. So the concept's been around forever and a day, and it's just, you know, Java eventually got big enough and, you know, thick enough or whatever, people jumped on and said, okay, add this one too. Same concept as, you know, C#, I'm sure. Independent of whether Java did it or not, I imagine C# would have eventually picked it up as well.
I see.
It's a concept that's been around, it's useful. What do you do? The core language moves only so fast because everyone's program breaks when it changes. But then I have all this other cool stuff I'd like to go do that, you know, it's not in the core language. What do I do? Well, you either throw it in a funny comment, and that puts a limit to how much program semantics you can add, or you get a little more clever, and the compiler supports the notion of a syntactic blob that it doesn't know what it means other than it's an annotation, and it can peel it apart, keep it floating around with and associated with the different things, associated with statements or with methods or variables or whatever. Some other language tool can read that out of in Java's case, out of the class file and do something with it. So, you know, not null annotations are sort of very common, popular things. Override. It's just a hint to say this, but if I blow the hint, the IDE will complain at me and say, hey, you claimed override, but I don't see the parent class, right? But the Java C compiler is just going to blow it off. And that's I think that's fine.
Tangentially related, Julia lets you like mark functions to be inlined, which is pretty cool.
that's been around since, you know, the early C days. Right, so inlining has this issue that it's, you know, it's a technology lifetime. As soon as compilers got good at inlining, no one cared to hit the inline button anymore. So why does Julia say inline here? Why do they have it in the language?
In terms of?
So mostly inlining is solved in the sense that if the compiler can deduce the target of a function, it can also deduce that it's sensible to inline or not. There are a very small handful of set of cases where the compiler gets it wrong, but also has all the knowledge.
Well, people writing more and more complicated code. So like we talked previously about these cases where you need to go through several levels of inlining to see the benefits. So I wouldn't say that it's quite solved, but because people write more complex code, but I agree with general gist of it.
It's the case that the compiler doesn't know the target in the hot inner loop. And so here the inline hint would be inline a very large chunk until I got all the way out to where I could see the type of the inner loop. And there I agree that we're not there, and then some sort of inline hint makes sense. But this has been like 20 years of inline does not make sense. There were 20 years where it did, sort of, 10 years where it made sense. 20, 30 years where it made no sense. Now it's back on making sense again. So I'm just probing, you know, the reasoning why. Particularly, it's not picking on you. Just probing why inline decision was made for Julia. There are almost always the compiler knows what the hell. It's pretty obvious with the inline. It's small. It's inside some loop nests. You know, there's a couple of very straightforward things to go inline. It's an allocator, so it's producing a new object. I want the strong types on, yada yada. There's a bunch of obvious heuristics you run. And that is what Hotspot's been run for with 20, 30 years with great performance out of Java. So no one cares for an inline keyword in Java. It's been inlining fine. Okay, now you come to this new world of these Scala languages, and actually happen in Java too, where you have these, you know, hot loops over large collections where the inner function is megamorphic, and you don't know what the target is. And now to get the target and to get performance, you have to clone the iterators that are nested however deep until you get a private guy. And it's a little more complicated, and it's less obvious to me, at least, what the heuristic is. But as a programmer, I can typically nail them, and suddenly I want the keyword again. And I'm just probing why you said, Julia has it, it's cool, but why does Julia have it? Fine.
Yeah, I think definitely not the one that has it, but I think for Julia, people actually use it, and like they consciously think about that when they build a function. Like, do I have to mark this for inlining?
I'm asking the question.
Yeah, it's a good one.
Why is the inline keyword helpful over what the compiler would do without it? When is the decision the compiler making about inlining in Julia code different from what the user thinks it should be, so that an override is actually productive?
I don't think Julia ever tries to inline or do any kind of profiling.
So, okay. I don't know what Julia's backends look like, but almost surely they back over somebody else's backend, such as LLVM, who damn well will inline the shit out of things.
Yeah, they use LLVM.
Yeah, okay. So almost surely there's tons of inlining going on already by the backend. And now the question is, did you need to do inline?
In C++, which uses LLVM, I sometimes wish for the call side inline. So this is pretty much the opposite of the current declaration side inline when I want to have precise control on the code size.
Yeah,
that's the way inline.
The Java problem as well. It's not really that I want to inline this function. It's when I want to have these call sites inline their targets.
Precisely.
So I can carry the precision down to the,
Exactly. I actually wonder why wasn't this the first inline decision in the compilers historically? Because the declaration sign seems weird even from the historical context.
I lived that era. It totally made sense at the time. It was you put keywords on function calls, on function declarations. You did not put keywords on call sites.
I mean, I remember prodding Turbo C++ compiler to do some inlining, but even then, I think I would have preferred call site inline.
You know, it could be. I'm just saying the easy hack in the compiler was you could put a keyword on the function header, And then the optimizer took the hint.
The simple string that could possibly work. That still rings true today.
Yeah, history. It is what it is.
Scala has a inline annotation that you can use at both a function definition as well as a call site to try to hint to the compiler to perform inlining. That's useful sometimes for higher order functions trying to avoid lambda allocation and stuff like that, where the JVM wouldn't naturally do it for you.
I tried really hard to get Scala to do high performance work while I was doing H2O, and I could not get the inlining to happen enough to get it to bake down to anything close to what Java was doing. Like the basic stuff for doing big data array math, Java was still 2x faster than Scala in every case, no matter how hard I tried. And I tried to get it just as perfect as Scala. People, do this and specialize that and inline here. No.
Yeah, it can be very, very difficult.
Yeah.
Yeah, I think once you get the ability to mark a particular call site as force inline, now you want to have not just a call site, but call site in the given context, because in different contexts, this call site, it might be called from different callers. And in some cases, it makes sense to inline, in others don't.
Right. So this is a case where you just keep marking the nested set of callers to get it to inline in the way you want. But the other people whose call site didn't mark don't have, they go to the shared copy. So you end up with a call site around a method. This guy gets inline in a private context because you also tag his call sites. This chunk did not and goes to the shared blob, and you have a few extra inlines because this guy got an inline because you tagged his inner guy because you were trying to get it in this context to be totally inline. You didn't care over here. But you end up with an extra copy, but that's not so bad. It's only bad if you had bazillions of extra copies because you've had some exponential growth. See, all these inlining issues have the same problem as the compilers always had, which is you can press that button too hard and you get exponential code growth, and then the compiler just dies trying to do code gen, like classic old school code gen. All these algorithms blow out for size and space, and then if they actually generate code, your performance sucks because you blow out your iCache. So there's moderation, all things in moderation. And if you give a user a tool like inline this call site, they will always, not always, somebody will always overuse it and then complain at you saying your performance sucks because I inline. Fine. I think you're right. Call site inlining is a call site tag is a good place. This is where you want to do it, not at the function. You want to do the call site. And then it's probably okay to go tag up and down the food chain, the call site chain that you want to tag, and you'll get some extra inlines on the call site path you don't want, but a few extra inlines is okay. Inline annotation. Okay, is that inline per function or per call site?
That's for both.
There is one for call site.
Yeah. If you take a look at the link there's an example of doing it at the call site.
Okay.
It also allows you to do the opposite, and if you have a function that's marked as inline at the call site, you can say no inline.
Yeah. As soon as you have one, you throw the other one in for free. That's
right,
not
sure. Of course, it all depends on you actually having the Scala optimizer option set up to actually perform the inlining for you. Otherwise, it won't happen, and it can be difficult to debug.
Yes. Well, that gets a different one. It's just, yeah. That's the reason I was all excited about coughing up the machine code that the JIT spit out, because ultimately you wanted to see what the hell it did do. And that didn't necessarily tell you why it failed inline, but at least it told you it didn't inline, so that's your bug, as opposed to it inline and you still suck, so something else is wrong. There's still work to be done for compiler engineers, that's for sure. Well, it's now 11. Anyone else want to chime in with something?
Yeah, I was going to go back to that to that comment of solved inlining. I think I can give quite a few examples where even if we know statically all the targets, it's still hard to decide that inlining is profitable. One of the examples would be, let's say we have a caller which has a new allocation and it passes it into some Kali. This Kali is pretty large, and well, let's say the frequency of this Kali relative to the caller is not high. It's just like one-shot call. But somewhere inside this Kali passes this new allocation down to a hot loop. And in this hot loop, we do, let's say, indirect calls on this argument and things like that. So just looking top down from the caller where we have this new allocation, it may not be obvious that there is this high benefit somewhere down the call graph. And like we know all the targets statically. It's just we need to analyze deep into the call graph and have some cost benefit model, not only for one call site, but for a group of calls.
So the hotspot heuristic here says the hot inner loop triggers the compilation. You crawl a stack looking for a break in the frequency distribution from hot to cold, because you want to capture the loop that that surrounds the hot call site. That did not necessarily take into account that the driving cost of the inner loop is an allocation which comes from, yet again, further out, which is exactly what you're saying. So this goes to the classic problem of the hot inner loop actually had a V call that went megamorphic or whatever I call, I don't care. And the type of that is crucial for performance. That's where you need to force inlining. And so you're exactly correct. This is the standard case we've all been talking about. How do you know where the type is known for the hot inner loop? Probably there's great compiler analysis now that we know that that's the right thing to look for, but at the time hotspot was done, the inlining decisions were, bottom up, just you had a frequency distribution split, and then top down using an analysis of frequency and a little bit of class hierarchy, but nothing deep about the hot inner loop for inlining. Once the compiler even knew where the loop was and who was in the loop and who was hot in the loop, he was past the inlining stage and went inline again. And that was sort of good for the time, but nowadays I claim we should incrementally inline, and the JIT should at least sort out what the hell's going on in the hot inner loops and decide if he wants to inline again. And then because he's inlining, he inlines either up to get a tighter, bound on the type coming in, or down by cloning the loop and putting out different versions of the loop. Yeah, here we go. Debuggability.
So the debuggability, basically, as a compiler developer, how do I fix wrong inlining decisions? If the context is proposal to use machine learning to analyze profitability of inlining in LLVM. I think there are pros and cons of this proposal, but one aspect I would like to be really informed about is how do I debug it as a compiler developer? Say I have a bug report and customer tells me that the function wasn't inline, and the policy to inline has been decided by a machine learning algorithm. Now, how do we reason about what was correct and what was not correct in the machine learning algorithm that decided to perform inlining or not?
So back up. So the problem here is that the approach you're taking is flawed from the get-go, and that's this inlining decision is not right or wrong. This inlining decision stands in the context of every other inlining that goes around. So it's all about statistical. Okay, so it could be the case that this guy wants this function to inline, and no one knows. He could be totally correct. There's a giant performance win. It could be totally wrong. It means nothing at all to his own app. And it could be everything in between, and it could be statistically speaking, it doesn't matter. And so the fact you didn't inline it meant that everyone else on the planet didn't freaking care. The hotspot heuristics were basically hand-tuned with experimentation, and they got pretty good giving other limitations about where you inline, where you don't. I think that's the right way to look at it. So you get some more holistic view. I have all these other functions I'm trying to decide inlining or not. I made one error in some cases. How do I deal with it? Okay, well, how do you deal with it in any sort of statistical analysis case? You have a giant corpus of functions, and you decide the inline or not, and you look at the overall performance metrics for them all. Unless you see a common pattern, like we were talking all along here about hot megamorphic calls that are nested too deep, your corpus tells you you're doing it right or you're doing it wrong.
Yeah, I think introduction of ML doesn't change the whole picture here, because even currently, all these inline heuristics, they are insanely complicated. And trying to figure out why a particular decision was made, well, there are some cost-benefit analysis, and it was tuned on given set of loads, which was analyzed by the compiler engineers, that this set of parameters is good. Well, taking ML is just automation of this process, which was previously done mostly manually.
Yeah, yeah. And the key metric here is that you have to have a standard load, because that's how you make reasonable forward progress. So you might claim the load was bad. You need a better load and a smarter load. You might need a bigger load, but then it takes time to go run the metrics. But you need a standard load to do performance work, and then you can start tuning things. Once you hit that domain, yeah, machine learning makes some sense. The law of knobs to turn. I believe at the time we turned them with sort of a classic state space exploration search. You know, they were hand rolled for a while, and then you start doing automated, but it was state space exploration with the, you know, hold all variables still and tweak one knob until it optimized, then hold it still and tweak a different knob.
So yeah, that makes sense. And I think that's actually a good point, that machine learning could be just thought of as generalizing what we already have. Those heuristics are basically special cases of machine learning models with coefficients already trained on manually by developers who came up with heuristics. But benchmarking is actually interesting. I wonder, are you aware of this paper? It recently came from Google, ASMDB, as in assembly database.
I've heard of it. Here, I'm trying to answer Tim's question here. You need another flag to unlock the developer options. There's a key to unlock the key to unlock the key. Sorry.
Okay. I'll take
so
a look.
ASMDB.
All right, so basically what was interesting in this paper, they are going company-wide profiling, and they found that a lot of cases that have been optimized on standard benchmarks or even micro benchmarks turn out to be not so good. And those are high-profile results, so functions like memcopy and memcompare, which have been for decades now optimized to death, and the optimization often looks like adding several different cases in memcompare function. You can branch on different factors, the size of the data, etc., etc. And those optimized glibc functions were great on micro benchmarks, but when you insert them into the real production workload, those branches bloat the code size so much that the instruction caches actually is going to push different code of the really hot applications out, and it's going to slow down the entire application. And in a sense, just looking at those micro benchmarks, you won't know what hit you, because it's all going to look great. It's going to even look like a very, very significant performance win to add those different vectorization factors and different unroll factors, etc., etc. But the moment you insert this into a real production workload, you are actually going to suffer a lot. So that's one.
I did this very thing a number of times, but always in more moderation than doing the endless unroll for iCache blowout. Like we're well aware of iCache blowout. It was a fun thing I did some years ago, quite a few years ago, looking at performance of different things. And one of them turned out that the layout of hot code in your iCache was not being tracked. And some of the hot code would land, enough lines of hot code would land on the same iCache line that it would start to blow out the associativity. And many of the iCache lines had very low usage, so there was basically spare lines on them that wasn't getting used. And your iCache effectively was 20% smaller than what you thought it was. And all you had to do was redistribute, relay out the code so that the hot code was smeared out over the iCache more uniformly. And that was the biggest win I'd seen in a long time out of an optimizing compiler. iCache blowout's a thing, and it matters. So yeah, definitely Hotspot has a bunch of heuristics. You're talking inline heuristics that conflated. A bunch of them are timed around don't inline because we're worried about iCache blowout. There's the yes inline please, and then there's the we done enough because we're worried about iCache blowout. This function's mid-sized and been JIT'd once already. Do not inline it into somebody else and have many, many copies of a mid-sized method because you get iCache blowout.
I think there's also a more general problem here that as a compiler developer, VM developer, we have some set of workloads we track, we analyze, and we tune the system on. But there's always a question how this set, like limited set of workloads, is representative of all the code being run. And I think this paper is demonstration that, yeah, the compiler was tuned on some set of benchmarks, not necessarily always micro benchmarks. Maybe there are some large scale applications as well, but in the end, it didn't work well for other applications. Yeah. And
Hotspot went through rounds of increasing. So the Hotspot team, while I was at Sun, and yeah, at Sun, went through rounds of increasing the size of the load so that we got more realistic load over time. It kept changing. You know, we did spec JVM 98, and then we did spec JVB, and then we did DeCapo benchmarks and a bunch of others after that, plus a bunch of internal Sun things and JBoss and WebSphere and whatever, and the load kept growing. So you kept getting retuned for larger and larger load sets. And things we had done carefully for JVM 98 like didn't matter anymore. So they got ignored, and whatever flags happened to them. Yeah, there's an issue where you need to have a realistic load. I'll agree. Okay, folks, now I'm going to call it. We're down to 6, but I hope to see everyone next time. Thanks for participating, and I'll throw the video link out as soon as Zoom lets me. All right, have a great week. Bye.
Yeah, thanks. Bye.